So I recently came across this awesome tutorial on lighting a simple scene in Unity, and I thought I would do the same using the new and improved Progressive Lightmapper. So in this video we'll learn a bunch about lighting and use it to put together this scene. Also make sure to check out the guy who made the original tutorial, LMH Poly. He has a bunch of really useful videos. This video is sponsored by Dennis Penjuta. Dennis is an awesome Udemy instructor and has just launched a new course, the Complete Unity 3D Game Development course. Throughout the series you'll learn how to create 6 completely different games. This includes Pong, Zigzag and Farmville. When you're done, you should have a solid understanding of Unity as well as programming in C#. You'll also learn how to create basic 3D assets using Blender. So to get started, simply click the link in the description and get a discount. Alright, let's get into the video. So before we start setting up lighting, there are a few things that we need to understand. The first one is global illumination. We all know that our eyes work by picking up rays of light. Unless we are looking directly into a light source, these rays of light bounce around between objects before hitting our eyes. Every time the light hits an object, it gets modified, absorbed, or sent out in a new direction depending on the properties of the material on that object. Because of how powerful modern computers are, this is something that we can now simulate, and the results can be incredibly realistic. In computer graphics, we split up this act of light bouncing around into 2 categories: direct and indirect lighting. Direct lighting is when light gets sent out from a light source, bounces once, and then reaches the eye. Here's an example of a scene with only direct lighting enabled. As you can see, objects not directly influenced by the light are completely dark. Indirect lighting is when light bounces off multiple surfaces before hitting the eye. Of course, theoretically, light will keep bouncing until it gets fully absorbed, but we can often get away by only calculating a few bounces, after which the remaining light waves will be so weak that they don't have much influence on the final image anyway. Now, Enlighten is a solution for delivering real-time global illumination. This is great if you have a lot of moving lights or objects in your scene, but often you want to calculate lighting beforehand, both to get more detailed lighting, but also to save on performance. This is called baking. When you bake your lighting, Unity calculates all the lighting values and turns them into large textures that are then overlaid on top of your objects. While you can use Enlighten to bake your lighting, it's much preferred to use the new Progressive Lightmapper. The Progressive Lightmapper is a path tracing based lightmapper, which means that it will realistically simulate lighting bouncing around the scene. It does this by gradually sending out light rays from the camera towards the light sources. This means that you can see the result as it renders in the editor, and you can adjust light properties without having to re-render the entire scene. So with that explanation, let's jump right into Unity. So here's a simple scene in Unity. I'm using completely default settings here. The only thing I've done is gone ahead and import 2 3D models. We have the room here, which is just a simple cubes where we can see through the back faces of the walls, and a monkey. He's cute, right? I've also taken my main camera and positioned it so it looks inside of the room. Now the first thing that we want to do is set up a few light sources. By default, every Unity scene comes with a directional light. I will simply go ahead and remove this. That's because I want this to be an indoor scene. So instead, let's create our own lights. Of course, we could go right click, light, and select one of the predefined lights, or we could simply create an object with an emissive material. And that's what we're going to be doing here. So let's right click, go 3D object, and let's select a plane. Let's also disable lighting in the scene view so we can clearly see what's going on. Let's set the scale of this plane to 0.2 by 1 by 0.2. Let's also reset its position. Let's rotate it by -90 on the Z here. So now it's pointing out from the left wall. I'm going to hold down Control in order to snap this plane. Let's snap it into the wall. Let's move it down to stand right on top of our ground. I'm also going to take it and move it out a tiny bit. We can use something like -2.49 just to make sure that it doesn't intersect with our wall. So right now our plane has a default material applied. Instead, we want to go ahead and create a material that will emit light onto the rest of our scene. To do that, let's right click in the project, go create, and let's create a material. I'm going to call this material orange light, and I'm then going to drag it onto our plane. On the right hand side here under emission, let's enable that. And here we can choose a color. I've already found an orange color that I like, so I'm simply going to paste it in here. You can of course use the same one if you want. I'm also going to set the amount of emission to 1.5. So down here we can see that it makes our material look brighter, but in our scene it's currently not really doing anything. First off, we need to make sure to re-enable lighting, but still nothing is happening. The reason why is that objects with emission won't actually emit light in real time. Now in order for this to show, we have to bake a light map. And to do this, we have to let Unity know that our light, as well as the rest of the objects in our scene, are all static. In other words, our objects aren't going to move, so we can safely bake a light map for them. To do that, let's select our plane, hold down Shift and select the room and monkey as well. Let's go to the top right here and select static. And now you can see here in the bottom right corner that Unity starts baking a light map. And right away we can see the result. This is by no means pretty yet, but we definitely have lighting in the scene. I'm going to rename the plane here to orange light. I'm going to duplicate it. I'm then going to go to the X position here and remove the minus to snap it to the other side. And I'm also going to rotate it around the Y by 180 degrees. Finally, I'm going to duplicate the orange light material. I'm going to rename it to blue light. I'm then going to drag it onto the light on the right hand side here. I'm going to select the color, and I have a blue color prepared as well. And I'm also going to go and change the emission to 2. Finally, I'll select the new light and rename it to blue light. So now in our game view, we can see that we have 2 lights and this simple scene. But it doesn't look too good yet. One of the reasons why is whenever you import a 3D object, you have to make sure that the object has light map UVs. In some cases, you can get away by simply selecting the object and enabling generate light map UVs. This means that Unity will automatically calculate the light map UVs for this object. If we hit apply on our room here, you can see not much changed. That's because when creating this room in my modeling software, I've already made sure to create UVs for it as well. But make sure to use this option if you haven't. But our scene still doesn't look that good. Let's try and change the lighting properties. To do this, we'll go Window, go under Lighting, and choose Settings. This will bring up the lighting window. First, because this is an outdoor scene, I'm going to go ahead and remove the skybox material. So I'll simply set this to None. Right away you can see this darkens our scene and gives it kind of a bluish tint. That's because the default ambient color in Unity is a dark blue. If your entire scene is indoors, there really shouldn't be any ambient lighting. All the lighting should come from light emitters within your scene. So we'll go ahead and set this to a complete black. We'll also make sure to disable real-time global illumination, because again, we want to only bake our light maps. And you can see right away our entire scene becomes dark. That's because so far Unity has been using real-time calculated lighting. And now Unity actually starts baking a light map. Again, the result here is not too impressive. That's because we want to configure our light mapping settings. First, we choose what light mapper we want to use. We of course want to change this from Enlighten to Progressive. Sometimes when changing between the two options, you have to go down and deselect Auto Generate, then go to the drop-down arrow and hit Clear Baked Data, and then we can once again enable it. You'll notice how the entire scene again turns black. And it might say it's baking down here, but the result is also completely dark. The reason why is when using the Progressive Lightmapper, we have to make sure to go into our emissive materials. So here's the blue light, and under emission change it from real-time global illumination to baked. I'll go ahead and do the same thing for the orange light. And right away you can see the light mapper working in our scene. You can also see that it looks very noisy. And after a while everything suddenly looks smooth. And the result is already much better. If we now go ahead and make a change to a scene, say let's move our monkey, we can again see this noise reappearing. What we're seeing is actual light rays getting sent out, and as more and more gets sent out, the noise gets reduced. And finally, when the light mapper has sent out all of its samples, it simply takes the result and blurs it. You can also see that because I have prioritized view enabled, the light mapper will actually render the part that we are looking at in the scene view first. This is super cool if you want to focus on a specific part of your scene. So now it's time to play around with some settings. And the first most noticeable problem that we want to get rid of is this weird seam running down the monkey's head. Now this seam is here because I've gone ahead and manually UV'd the monkey, and this is one of the places that I decided to put a seam. But of course we want to make this as hard to notice as possible. And one of the really cool tools that we have here is what is called seam stitching. This is something you enable per object. So if we go ahead and select our monkey, switch to the inspector, and go under the mesh renderer under lighting, here we have a separate category for light map settings. And here is a property called Stitch Seams. If we now enable it, you can see that immediately the seam gets blurred out and becomes way less noticeable. I definitely recommend turning that on for most complex objects. And our lighting actually already looks okay. One of the things that we can do is easily decrease the light map size. This is simply the end resolution of our texture. And because our scene is very small, we can definitely decrease this to 512. As you can see, the end result is pretty much the same, and we've just more than half the size of our light map. We can also choose whether or not to compress the light map. This will heavily reduce the file size, but it can also add a lot of weird artifacting to the lighting. In fact, we can see an example of that right here. These weird bands are because of compression on the light map. So let's try and disable it. You can see right away our light map increases in size, but the banding is now gone. We can also see on the side of the monkey here, on the ear, we're getting these weird purple colors. Now these are definitely not supposed to be here. This is what we call bleeding. It's when data from one part of the light map bleeds into data from another part of the light map. If we switch to the Global Maps tab here, we can actually see the two textures that were generated for a scene. Notice how we can recognize different parts of the scene in these maps. We have different walls from the room, and we have different parts of the monkey. If some of these elements start to bleed into each other, we get this weird result. So to try and get rid of this, I would start by increasing the light map padding. Let's try and set this to 8. Right away, we can see that the problem still occurs. So let's now try and increase the light map resolution. Let's try and increase it to 100. Now that definitely helped, but we can still see a tiny bit of bleeding. So let's try increasing them a tiny bit more. And there we go, the problem is now gone. Keep in mind that every time you increase the light map resolution, it will also take longer for your light map to bake. So some of these settings you might want to leave fairly low while adjusting, and then when it's time to bake the final result, you can bump them up. This also applies to the number of direct and indirect samples. Sample is basically just another word for ray. So this here is the number of rays that we send out per texel in order to determine the direct lighting in our scene. And this here is the same but for indirect lighting. In other words, if we go ahead and increase these, we should get greater detail in the result. We can also adjust the number of bounces that we want to calculate. We could say set this to 3. And this could take a while, so you might want to go off and do something else. And you can see the result is a much smoother, less noisy light map. And the lighting will definitely be more precise. This is always one of those settings that I just leave by default when I'm setting up the scene, and then crank all the way up when it's time for a final render. Especially because the number of direct samples and bounces don't have any influence on the size of our light map. They just increase the time it takes. So I'm gonna set these back, and finally I'm going to enable something that will make everything look much better. I think this is everyone's favorite setting to enable. I'm of course talking about Ambient Occlusion. Ambient occlusion is the shattering that occurs between two nearby objects. As you can see in the corners of a room here, in the crevices on a monkey, and where our monkey sits on the ground. So right now it's maybe a bit too much. I'm going to decrease it to 0.1 and also decrease the max distance to 0.7. Finally, if you find errors in your light map that you just can't get rid of by adjusting these settings, it might be because it happens during Unity's filtering stage. This is why Unity takes the fairly noisy light map and applies some post-processing in order to smooth it out. Luckily, we can adjust how Unity filters the light map. To do this, we go to Filtering, and you can see what happens if I disable this. This is the finished light map in its raw form. From here, we can go under Advanced, and we can add different types of filtering. I find that in 90% of cases I use Gaussian, and here you have the possibility to dial down the amount of filtering both for the direct and indirect lighting as well as the ambient occlusion. For indoor scenes, I often have to go in here and decrease the filtering on the indirect radius. As you can see, the scene still doesn't look noisy, and it often removes weird lighting glitches. But for this scene, we can simply keep it at auto. Finally, if your scene is overall too dark, you can increase the indirect intensity or give your entire scene a boost using the albedo boost. One of the questions that I get asked the most is how do you add glow to your lights? They're currently shining onto the environment and that's fine, but most of the time when you look directly at lights in real life or through a camera, they will have this sort of glowing halo effect. The answer is we don't actually add this through the lighting system. Instead, we use post-processing effects. To do that, we'll go to the Asset Store. We'll search for post-processing, select it, hit import and import again. Then we want to select our camera, go to the inspector, and here we want to add a component called the post post-processing behavior. This will enable post-processing on our camera. We can then switch to the game view to see the result. We'll right-click in the project panel, go create, and we'll create a post-processing profile which will store all of our settings. We'll call it CC for color correction. Select our main camera and drag in our CC object. And now when we select our CC object, we have all of these different post-processing effects. The one that creates glow for our lights is the one called bloom. And this might be a bit too much, so let's open up our bloom. Let's decrease the intensity to 0.3. And let's also decrease the radius to something along 2.8. And while we're at it, we can also add a tiny bit of color grading. Let's enable that. Open it up and we'll change the tone mapper to filmic. We'll also increase the exposure a bit. And maybe we want to decrease our bloom even more. And finally, we can go in and add a vignette. And we probably want to decrease the intensity on this one as well. So there you go, that's the basics of lighting a scene in Unity. That's pretty much it for this video. If you want to learn more about lighting, such as how to set up real-time lighting in Unity, definitely let me know in the comments. Also, make sure to check out the complete Unity 3D game development course. Simply click the link in the description to get started and get a discount along the way. Other than that, thanks for watching and I will see you in the next video. Thanks to all of the awesome Patreon supporters who donated in December, and a special thanks to Judaman, Beffio, Infinity PBR, Uri Omer, Hans Hoftoon, Cyborg Mummy, Derek Heemskirk, Mur, Faisal Marify, Beardo Die, Double Tap 45, James P, Dan Evans, Thomas Worley, Superman the Great, John Beauregard, Cole Cabral, Jason Latito, Alex Rakitsky, Suni Jakobsen, James Rogers, Robert Bund, Rob Farn, and Erasmus.